Given that benzene is aromatic and therefore especially stable, we might expect that other molecules with similar structures will be similarly stable. It turns out, though, that this is not necessarily the case. Cyclic molecules with alternating single and double bonds, like benzene, are called annulenes. The following three molecules are all annulenes, but of the three, only benzene is especially stable. Cyclooctatetraene is about as stable as a typical alkene, and cyclobutadiene is actually more unstable than a regular alkene. Those compounds that are more stable than expected are termed aromatic, while those that are more unstable than anticipated are called antiaromatic. Finally, a compound with no particular stabilization or destabilization is called non-aromatic. It is essentially normal. In this video, we'll learn how to make the distinction between these three classes of molecules. In the early 1930s, Erich Hückel developed guidelines to identify aromatic, antiaromatic, and non-aromatic compounds. There are essentially two criteria that must be met in order for a molecule to be aromatic. The first criterion is that the molecule must be cyclic, it must have a p orbital on each and every ring atom, and it must be planar. In other words, to be aromatic, a molecule must contain a continuous cyclic array of parallel p orbitals. If a molecule does not meet this criterion fully, it is non-aromatic. The following three molecules fail to meet the first criterion of Hückel's rule in different ways. For example, the first molecule is simply not cyclic. It fails the first criterion and is therefore non-aromatic. The second molecule, while it is cyclic, does not have a p orbital on every ring atom. The two carbons on the right-hand side of the molecule are sp3 hybridized and therefore do not have unhybridized p orbitals. This molecule also fails the first criterion and is non-aromatic as well. Finally, the third structure is cyclic and has a p orbital on every ring atom. However, it is not planar, so the p orbitals are not all parallel to one another. This molecule also fails the first criterion of Hückel's rule and is non-aromatic too. Remember that non-aromatic is not necessarily a bad thing. It is essentially normal. These molecules have roughly the stability you would expect from typical alkenes. For molecules that satisfy the first criterion, specific numbers of pi electrons result in aromaticity, while other values result in anti-aromaticity. Now, rather than compiling all of these values into a long exhaustive table, Hückel formulated a simple algebraic expression that allows us to determine whether a molecule has the necessary number of pi electrons to be aromatic. And that expression is 4n plus 2, where n is any integer greater than or equal to 0. Some Hckel values are given in the table below. For instance, when n is equal to 0, then 4n plus 2 is 2 pi electrons. If n is equal to 1, 4n plus 2 is 6 pi electrons. If n is equal to 2, then 4n plus 2 is 10 pi electrons, and so on and so forth. It's very important to note from the outset that n has no physical meaning. It is not derived or predicted from the structure in question. Instead, we simply substitute integer values of n into the equation 4n plus 2 until one of two things happens. We will either match the number of pi electrons present in the molecule, or we will miss the number of pi electrons present in the molecule. There are two examples on this slide that allow us to test the second criterion. The first molecule shown on the left-hand side is benzene. It passes the first criterion because it is cyclic, it has a p orbital on each of its 6 ring atoms, and it is a planar molecule, so all of the p orbitals are parallel to one another. So after establishing that we pass the first criterion, we move along to the second criterion, and we look for a 4n plus 2 number of pi electrons. Benzene happens to have 6 pi electrons shown in red inside the ring. Well, 6 happens to be a 4n plus 2 value when n is equal to 1. Therefore, benzene is aromatic. It is especially stable. In contrast, we have cyclobutadiene on the right-hand side of this slide. Cyclobutadiene also passes the first criterion. It's cyclic. There is a p orbital on each and every ring atom, and the ring is planar, so all of the p orbitals are parallel to one another. However, cyclobutadiene has only 4 pi electrons shown in green inside the ring. There is no integer value of n which will yield a value of 4 from the rule 4n plus 2. This is instead a 4n value of pi electrons when n is equal to 1. Having a 4n value of pi electrons makes this molecule anti-aromatic, or especially unstable. Let's take a moment to talk about planarity. Annulenes that have 8 or more carbons are large enough so that they can bend out of planarity if it is advantageous to do so. What I mean by that is the following. If bending out of the plane would deprive a molecule of aromaticity, it will not choose to do so. It would not want to throw away the opportunity to be especially stable. On the other hand, if bending out of the plane prevents a molecule from being anti-aromatic, it will do so. It will essentially elect to bend out of the plane in order to avoid an undesirable fate, being anti-aromatic and being especially unstable. Cyclooctet opportunity issue of planarity. The molecule is drawn in 2 different ways on this slide. The first drawing shows what cyclooctatetraene could look like if it were planar. The second drawing shows the molecule when it has bent out of the plane. Let's first consider cyclooctatetraene as though it were planar. If it were planar, the molecule would pass Hckel's first criterion. It would be cyclic, with a p orbital on each and every ring atom, and we're making the assumption that it's planar. We would then pass to the second criterion, where we would count the number of pi electrons, which in this case is 8, and they are shown in green inside the ring. This is a 4n value of pi electrons, which would make the molecule anti-aromatic. Note that that is an undesirable outcome. Anti-aromatic is especially unstable. The molecule would prefer to avoid this fate, if at all possible. Happily, cyclooctatetraene is large enough, having 8 ring atoms, that it can bend out of the plane if it would be advantageous to do so. So now let's consider cyclooctatetraene that has bent out of the plane. As a result of doing so, it will fail Hckel's first criterion. And remember, molecules that fail Hckel's first criterion are non-aromatic. They are neither especially stable nor especially unstable. They are essentially just normal. And this is a better outcome for cyclooctatetraene than if it were planar, which would make it anti-aromatic. So the bottom line is that cyclooctatetraene does choose to bend out of the plane so that it can be non-aromatic. The next video in this series will continue our discussion of aromaticity with other, larger annuline.